Right. Okay. So this paper is about runtime behavior generation. Runtime behavior generation is a newish application area for LLMs in the space of video games, which should be interesting because game developers have been dealing with generative systems for over 40 years at this point. So the agenda for this talk is, first I'll be defining what exactly is runtime behavior generation. I'll then be showing that it's possible, and we'll wrap up with some results from interviews with developers about what they think about all this. But before I can define runtime behavior generation, I first have to define the sort of parent topic in the space of games, which is procedural content generation. And here, PCG just means generating game content with an algorithm instead of doing it manually. And so as an example, I'm going to hope that most people here have heard of Minecraft. It's a game where you build and place blocks in this big virtual world. And crucially here, the world is generated by an algorithm. So when you start a new game in Minecraft, you actually hit a button that says create new world. And then you see this animation, and that's an indicator that an algorithm is deciding where everything in the world is going to be, not a developer. And the upshot of this is that now every time anyone starts a new world in Minecraft, they get a completely new world, and they can walk as far as they want in any direction, and it keeps generating. So Minecraft came out in 2011, but PCG has been a big thing since at least the 80s. And in that time, game developers have figured out ways to procedurally generate lots of stuff. So they can generate textures, models, sounds, dungeons, entire worlds in the case of Minecraft. But the one thing that's been historically difficult is behaviors. And so to keep the Minecraft example running, Minecraft has this mechanic where you can place objects into a brewing stand, and then you make potions. And each of these potions roughly corresponds to a behavior. So the behaviors being how objects in a world act and interact with each other. And so if I drink a potion in Minecraft, maybe it'll give me night vision or fire resistance, something like that. And Minecraft can have infinite virtual worlds, but it only has a finite number of potions. So what's actually preventing us from having an infinite number of potions? Like if I could drag any object or combinations of objects into this brewing stand. Well, the tricky part is that if you want an infinite number of potions, you now need, depending on how you implemented it, either an infinite or a near infinite number of behaviors for each of those potions. And there's just no way for a developer to manually create all of them. But we know that LLMs can understand game environments. So if LLMs could create the new behaviors, then we can solve this problem in a similar way to how Minecraft solves its world generation. We just package an LLM with the game, and then at runtime it can generate new behaviors as needed by the player in the same way that Minecraft generates a world as it's needed by the player. So when we talk about runtime behavior generation, this is the sort of thing that we mean. There's two big questions when we start talking about RBG. First, can we even trust LLMs for this task without developer supervision? And then if we can, historically, runtime behaviors have been something that developers had full control over. So how might developers navigate an environment where now any part of the game could be generative? What even is the game then? So to explore this concept, we built a tool which we call Grommet. Grommet is a LLM-powered RBG system for the Unity game engine. It works like this. So this is a simplified diagram. We'll get into some detailed examples later. So first, the user is going to trigger the interaction in some way, and then that prompt, that trigger, along with the information from the Unity scene hierarchy, gets sent into a LLM prompt template that is going to ask the LLM to generate a new behavior by making some C# code. The LLM spits out some C# code that gets compiled at runtime, added as a behavior to the game, and the player is going to experience that and maybe generate more behaviors. And if you're interested in why it's called Grommet, this is why. There's a scene from the Wallace and Gromit TV show where Gromit's laying track for the train as the train is running. So we made 3 demos for Grommet, but I only have time to talk to you about 2 of them. So if you're interested in this, please read the full paper. The first demo I want to talk about is the escape room demo. So here, Grommet is going to implicitly generate scene interactions if they're undefined as needed by the player. So here the player is trapped in an escape room. They're told to find a key to open the door. And there's a lot of different objects in this room, some of which have defined interactions. So the key opening the door was predefined by the developer. But most interactions are still undefined. So if the player takes this torch and walks over to this bookshelf and tries to interact the two, that's an undefined interaction. If we didn't have RBG, maybe this is the point where the player character would say something like, that didn't work, or I don't know how to do this. If we have RBG, then we can simply invoke Grommet, tell Grommet, and Grommet knows that there's a torch object. It's interacting with a bookshelf object. It can then query the Unity scene to get the name and description of these objects and use that to fill out a prompt, which it then sends to an LLM asking for a description of what should happen and then the behavior of what should happen. So here the LLM has decided that if you use a torch on a bookshelf, it's going to burn the bookshelf down with the torch, and it implements that behavior by deleting the bookshelf. So that behavior is now part of the game. So without any more invocations of Grommet or an LLM, the user can just use this torch to burn down the rest of the bookshelves and is able to do this to find the key more quickly. So this is an example of how we can use Grommet to sort of influence all interactions in a game as they're needed. But we're also curious about what happens if you just want to use RBG to implement a single game mechanic. That brings us to our second demo. The adventure game demo has the player navigating through a dungeon while fighting some monsters and solving some puzzles. And only one of these mechanics is generative. So the spell mechanic in the adventure game is a generative mechanic. The player is a wizard, and they can cast spells, and they can combine spells to make new spells. So the initial set was all made by developers, but when you combine two spells, that combination is defined by Grommet. But then there's this non-generative mechanic, this puzzle mechanic, where the player is going to hit these switches, and it opens and closes doors. And so the dungeon's a bit of a labyrinth that the player has to navigate through. So here's an example of the generative mechanic. So if the player takes this air spell and tries to combine it with a fire spell, that interaction's undefined. So again, we're going to invoke Grommet, and kind of similar to before, that interaction gets sent to a prompt form along with some context from the Unity scene. Here the LLM is going to generate the code or the behavior of this new spell, but it also chooses an emoji for the spell and a name for the spell. The code gets compiled at runtime, and everything gets sent back to the game. So here, everything from the name Firestorm to the emoji to the particle effect was all chosen by Grommet at runtime. So now that we have our demos, we wanted to evaluate how does Grommet perform. So we generated, for the escape room, we generated a cross product of all possible interactions in the escape room. And then we generated about 200 spells for the adventure game. And then we classified the resulting behaviors. So the most common result was for Grommet to generate a novel interaction. So this is a new interaction or spell that you could look at and say, yeah, I guess that makes sense given what the context was. A smaller but significant portion of the time, Grommet ran into some sort of error. Although I should say that the game never crashed due to compiler or runtime errors. From the player's perspective, this usually looked like they tried to do something and then just nothing happened. An even smaller portion of the time, Grommet did what we would call a high-impact interaction. So this is a novel interaction that worked, and it also had a large-scale impact on gameplay moving forward. And so high impact here doesn't necessarily mean good, which is something that we can talk more about when we get to the developer responses. So we interviewed 13 game developers from a mixture of AAA, indie, student, and hobbyist backgrounds. The interviews were 60 minutes, and we showed them the Grommet demos and discussed their thoughts on RBG and how they might use it. And we learned a whole lot from game developers. I don't have time to go into everything here. Again, this is the full paper if you're interested in more. But I want to highlight just one point that came up, which was a lot of developers were concerned about runtime behavior generation overreaching its bounds, so that they'd use it in one mechanic, and then it would somehow influence other mechanics that they didn't want it to have influence over. So an example is participant 2. Mentioned that they were working on a horror game, and they thought maybe a RBG-based puzzle mechanic might be fun for this horror game. But they were concerned that they were spending a lot of time on like this monster for the game that they were making, and they were worried that somehow this puzzle mechanic would allow the player to either skip past the monster or change how they were interacting with it in some way. And so they said, I like making games, and creating rules is a big part of making games. I would like to be the one doing that and not giving it away to a tool. And so this made us look at the adventure game demo, which, if you'll remember, has this generative spell mechanic and this non-generative puzzle mechanic. And we realized that if you combine spells enough, you can make stuff like this lightning dash spell, which allows you to teleport through walls. And if you can teleport through walls, you don't have to solve the puzzle. So this is a clear example of a generative spell mechanic overreaching its bounds and allowing the player to skip past this puzzle mechanic, which is exactly what the developers were worried was going to happen. And so developers had a lot of ideas on ways in which we could put guardrail systems on the LLM generation to make sure that this doesn't happen, things from fine-tuning the model to just calling the RBG system less often. Another approach that was interesting was there was a few developers who just thought that maybe you could use RBG in situations where these high-impact interactions are less problematic. So participant 12 had an idea that you could use RBG to better communicate with communities that you're not familiar with when you start your development process. So they had the idea of you'd make a beta version of your system that has generation enabled. You'd send it to your potential users, and then you could use what behaviors they generate to inspire your next iteration of the product. And maybe the final version doesn't even include any RBG. Participant 5 had a similar idea where they talked about this infinite open alpha sandbox where players are constantly generating new behaviors and a team of developers is constantly in the background trying to fix the most broken ones. And I like this quote from them. They said, "I think given how interesting and powerful this is, they, the players, would be happy to tolerate a level of jank and strangeness." So if you have any takeaways from this talk, it should be this. First, runtime generation is possible with current LLMs, and it has the potential for large-scale impact. Second, if left unchecked, RBG can impact game mechanics outside of its initial space. Third, some developers want guardrails to control generated behaviors, and others suggest reframing the game so that high-impact interactions are less problematic. And finally, I'd like to point out, we were talking to game developers, we were talking about video games. I think a lot of these points that they brought up could be applied to other situations where we have these, where we're using generative systems in situations where developers have less than ideal control over them. Before we go into Q&A, again, I'd like to thank all the authors on this paper. Myself and Isabel Lee are looking for PhD programs. Han Wang and James Smith are looking for postdoc positions in AR/VR and teaching and research positions respectively. And Bjorn Hartman is looking for PhD students. And if you scan this QR code, it'll take you to a link tree that has the paper and then all of our personal websites on that. Any questions?
Thanks for this great talk. We have time for short questions.
Okay. Thank you for your great talk. I'm Lee from BUPT. And my question is, how much does your system rely on the capabilities of LLMs? Assume you can do other stuff using the GPT-4o. Can you use smaller models that maybe they can run on your laptops to do other things? Thank you.
Are you like asking if you could use like smaller scale models to do this sort of? Yeah. So that's not something we looked into. I think it sort of depends on. My intuition is it might depend a bit on the model. I think we used GPT-4, and I think a lot of why it was able to do what it was because people like talking about Unity like online, and it was probably trained on that information. So a lot of the basic Unity stuff, the model already knew, and that was part of what was enabling this to all happen. So depending on what model you have, if it doesn't have that information, it might be harder to make.
Hello, Long Pan from National Taiwan University. Yeah, congrats to the Best Paper Award, and yeah, well deserved. I really like this award. This is my favorite paper this conference. Yeah, and I really like the ideas, and I also see the potential of using LLM to actually generate, do procedural generation, actually generate like several, especially the behavior between objects. So I'm actually very curious that how you see, because yeah, several game objects, like as well as the experience itself, is mimicking the like physical experience as well, right? Like escaping room, for example. There are also like physical escaping room if you have attended some of the escaping room experience before. So I'm wondering if this system can be like further generalized to actually connect things in the physical world. Because you can see that some of the behaviors in the virtual world actually generated by the LLM actually very similar to the physical behaviors as well. So I'm just thinking, but definitely there are some like fantastic effects or like more magical effects that can happen in the virtual world. But I'm just wondering, maybe that the LLM can actually figure out like both the virtual behaviors and the physical behavior and try to connect them together. How do you see about this?
Yeah. So. Yeah, I think that's a definitely interesting direction to take this. So a lot of the games that have sort of similar mechanics to this sort of thing, historically, like a way to do that might have been to create this very detailed physics system inside the game and have that mimic the world. So maybe the torch is able to burn down the bookshelf because like the game knows what fire and wood is and is somehow able to handle that. So I think, like you said, like one of the advantages of having this be LLM based rather than physics based is that these sorts of more magical or narrative interactions can be managed properly. But yeah, definitely some way of integrating this with like real world systems would definitely be interesting. Some sort of, yeah.
All right. Thank you so much, Nicholas.